Okay, this is the circuit of the DynoBat as it's built for the moment, the prototype. Um, there is a small circuit here which generates about 50 hertz. Actually, it's more like 48.3 hertz or thereabouts. But for a first try, that's okay. And then this circuit, the oscillator in fact, generates pulses which, or rather a wave form, which drives this power transistor. And this power transistor sends an amplified voltage wave through a small transformer, and in fact through the secondary of the transformer. So the transformer is actually the load. Now the input voltage of the power transistor is around about 18 volts or thereabouts. It's I think sufficient voltage to be used to generate the final voltage that we would like to have, which is around about 90 volts, at least theoretically. Now, the voltage I actually get out of this experimental circuit is something like around about 54 volts. As you can see, it fluctuates a little bit, but it's around about 54 volts that I get out of it. The waveform that goes through the transistor looks very much like this. I hope you can see it. Let's switch this off and this. So this is the waveform that drives the transistor, and this is the voltage that I get out of the primary of the transformer. So as you can see, it's pretty close to 54 volts, which turns out to be 3 times 18 volts. Now there is a weird thing about it, namely the transformer is a transformer which has a ratio, a transforming ratio of around about 20 times, by which I mean that the output is a maximum of 9 volts, 2 times 9 volts, and the input voltage of the primary is 220. So if you calculate that, that gives about a ratio of 20 times. Now there are a few things that I need to find out first. First of all, the power transistor gets quite hot. Yes, it's quite toasty. I'm using a low-pass filter to cut off any residual spikes and all that, and all sorts of harmonics and all that off. So the low-pass filter is not ideal for the moment. It's around about 212 hertz. You can see the calculation I used to design the cutoff, the low-pass filter. As you can see, it's quite an easy setup. Yeah, you have an input resistor and a capacitor which goes to ground, and the voltage in goes here and the voltage out comes here. And it gave the waveform that you saw a little bit earlier. Now, a way to see a low-pass filter is like a sort of a short circuit for high-frequency pulses. In effect, a capacitor functions like a short circuit for wave-shaped voltage, and specifically for high-frequency waveforms. So it lets through only about 50 hertz or well, anything between, let's say, 50 hertz or a little bit less than that, and up to around about 212 hertz. So the reason why I actually use the low pass filter is to cut off any spikes and any harmonics and all that, so to get a sort of a clean wave to drive the power transistor, and also sort of to clean up the waveform in general, you know. And the way I calculated the cutoff frequency was by using this formula. The cutoff frequency is 1 over 2 times pi times the resistor and times the capacitance in farad. Yeah? So if you use a 1.5 microfarad capacitor, as I did, you need to multiply it by 10 to the power minus 6 to get it in farad. Now, if you calculate this, you'll see that you'll find a value of, I think it's 212. So the cutoff frequency, and by that I mean the frequency at which the filter starts to really attenuate significantly the signal, is 212 hertz. So anything below 212 hertz passes through almost unmodified. Right. So one of the issues I have is that if I drive the power transistor with about 18 volts, and I put the output voltage through the secondary of this transformer, which by the way is around about 55 ohms, then I get an output voltage of 54 volts, which is not too bad, but still a bit too low. Okay, a final update to close off the experiment for tonight. I burned through 2 of these power transistors. Okay, hang on, it doesn't want to. Yeah, so I burned through 2 power transistors, unfortunately, and for one inexplicable reason, my other multimeter just stopped functioning. Now, I don't think it's because of the voltage that came out of the transformer, although of course one never can tell, but it was set, the other one I mean, was set on the 1 to highest voltage setting, and anyway, at least according to the manual, it was surge protected. So I don't think my circuit blew my multimeter, so it's just an unfortunate concurrence of well, circumstances. Anyway, I do know more or less why the power transistors blew. Um, to drive the transformer, you need to put quite a bit of, well, I would say, current through it. And I neglected to cool the power transistors adequately. And the result, of course, was that after multiple switchings on and off and on and off, and without letting them cool properly back to their to room temperature, well, they degraded, and apparently at a certain moment they just popped. And in fact, one of them was so hot I burned the tip of my finger when I wanted to feel how warm it was. So there you go. I blew 2 power transistors. Okay, no problem. Let's not forget, this is after all an experiment. So what I'll need to do is to find out a way to drive the transformer without blowing the power transistor, obviously. Also, unfortunately, I can't show it right now since I ran out of driver transistors, is that by tweaking the cutoff frequency of the low pass filter, I managed to raise the voltage all the way up to almost 80 volts. So yeah, so there you go. I need to tweak the low pass filter frequency, and I also need to tweak the the driving voltage and the cooling of the power transistors, because if I don't tweak those 2 things, then I'll just keep on blowing up transistor after transistor, and of course that isn't the goal. So that's it for now. Let's say the result is mixed, as I thought it would be, but we'll see. So hang on for the next update. See you soon.